Hello, welcome to my talk on a coroutine task called lazy task. I will explain that a little bit, but before doing that, let's go on my lovely slide. I'm Dietmar Kühl. I work at Bloomberg since a fairly long time. I like it. I work on real-time market data distribution. Everything in our world is asynchronous, so I'm interested in asynchronicity. That said, none of the things I'm presenting here is actually used in production in our world at all. This is, I want to get there, but I'm not there. When you have questions, please ask and shout out. I may not see a hand. Shouting out is probably fine. And yeah, the other thing, a little bit admin thing, I'm very excited about this. And as the QR code leads to this page, which has more of the examples on. If you're interested, you can look at the examples, and they are on Compiler Explorer. They can actually experiment with them. So the library I've implemented for this is all on Compiler Explorer, and you can try it out there. It was not put by me over there. It was put by primarily Darius Nito. So thank you very much for that. And then, yeah, so the objective, why I'm talking about what I'm talking about. C++20 gets SUT execution, and SUT execution is quite exciting, and most users probably want to use coroutines, pretty much what I'm presenting over here. And so the objective is to create a coroutine task library, task for the standard C++ library. Unfortunately, I think as a committee, we goofed up, or I goofed up, because I didn't realize there was miscommunication in the sense of who's writing the coroutine proposal. There were people who said, oh, I'm going to write a coroutine proposal, and well, it didn't come, and eventually I went and kind of, all right, if we want to possibly have a chance to get it into C++26, I have to write the paper. I'm not the expert on coroutines. If people go on a task thing, if people think what I'm doing over here is entirely crazy or is missing crucial stuff, I want to know. It's not that I want to defend what I'm having here. It's more like I want to present what I came up with the help of lots of people. I basically said, oh, I'm going to write the paper. And then all people come out of the bushes and said, oh, you need to do this and this and this. And all of these things I would never have thought about. So, and that thing is important. Unfortunately, whether the coroutine task makes C++26 or not, it looks unlikely at the moment. I hope it does. We may still sneak it in late, but it looks unlikely. So what I'm presenting here, you may need to wait for a long time or use from the Beaman implementation. Okay, so yeah, the motivation why I think a coroutine task is crucial is composing work into algorithms is unfamiliar to most. I'm not saying it's unfamiliar to everybody. Some people do that, prefer to compose work using a functional style of composition. But as far as I can tell from my colleagues, most of the people go kind of, not so much, I can only read it if it is kind of looking like a sequential piece of code. And that's pretty much what a coroutine task gives you for asynchronous stuff. You can write, instead of writing lots of callbacks, you write something which looks like a function, it's a coroutine, and you just put core keywords in, and everything is good. So it's one of the motivations for having a task. There's a secondary motivation, and that is the standard library does not have any type erased sender. As it turns out, coroutines are type erased. So a coroutine task provides a type erased approach to implementing asynchronous work. So this is good enough for me. And then I don't know whether everybody knows how sender-receiver works who is here. Maybe they do. This is the entire slide I have on that, just to bring people up to speed on the very basis. A sender is nothing else than an entity which represents work. It has as properties pretty much something which is called completion signatures, abbreviated over here on the slide. to fit it on, and it's actually not quite accessed normally like that. But you basically get something like a return type. So the completion signatures is a generalization of return types, where you can have one or more success completions, set value, which can get 0 or more arguments. So you can have multiple of these, and the work chained onto that needs to process all of those. Likewise, you can have 0 or more set error completions with different types. And finally, the last one, which is missing parentheses, is, and I'm inconsistent with writing the type or not. It's actually all should have an underscore T and parentheses. The last one, stopped, is for cancellation. This is something which functions obviously do not have. You cannot cancel a function from the outside because you're sequentially running. But if you have asynchronous work, you have something which is possibly just sitting there, and you can tell it, oh, stop what you do, or you may have a busy loop and something else finished already, and you go kind of, oh yeah, we don't really need that, stop that. And the set stopped is basically a way to indicate I was cancelled, or I came to the conclusion I don't need to do the work. I didn't produce an result or an error, I just didn't run to the end. So this is pretty much what Robert in his presentation earlier this week presented much nicer actually. Okay, and then the next component to sender receiver, they will show up a little bit in my talk as well, is a receiver. This is basically the generalization of a callback where completions go. So receiver, the way it works is it has overloads for set value, set error, set stopped, which are called by senders under the appropriate conditions. And there's a second fairly important property, and that is you can get an environment. And if you cannot get an environment because the receiver does not provide it, the system actually goes kind of, all right, fine, there's an empty environment. So all receivers implicitly have an environment. And finally, the third entity is an operation state, which is basically an entity which consists of a sender, which just represents the work, and the receiver, which represents the completions, put together, stuck into memory until, and it stays there and stays put once it gets started until something completed. So these are the components. Okay, now on to the actual interesting bit. And here's a simple display of a sender. This is using actually an awaitable, a suspend never. This is in a standard library. It's not since longer. This is not a sender, but it can be seen as a sender or the other way around. In this case, actually, senders can be seen as awaitables. So the coroutine can await senders. All the examples I have of senders will be just sequential ones because I'm not interested in the asynchronous aspect over here. Just want to describe the interface. Where it says just, it could be some other work, it could be passage of time, which then actually would be asynchronous, or reading data, or whatever it is, something which is just asynchronous. There's a few other things which this slide already shows, and that is a task. Over here, basic is used with async wait. Async wait takes a sender, which basically means a task is a sender. So you can basically chain them if you want to. You can co-wait a task, or you can use a task with any of the other sender algorithms. This all composes. And from a representation point of view, a task is sender. So the way it starts off, once you have created a task, like when calling basic, we have our task entity, and there's somehow a coroutine frame which contains a promise. So the task itself does not have much of an interface. The only interface it has, it can be combined with the receiver using connect to actually form an operation state. And once an operation state is formed, actually the ownership of the coroutine is transferred to the operation state, and the task goes away, which also means you cannot restart a task, which is partly down to you cannot restart coroutines either. So they are only move constructible and can only be started once. Okay, now on to what happens in there. It's kind of important, how do results from senders map into the results of co-await. And there's basically three cases. The first case, the coroutine, the awaited thing doesn't return anything, it returns void. So just completion signature is just set value of t with no arguments. In which case, if co-await gets something which is just has no arguments, it doesn't get a result, so it's void. If there's exactly one argument in the set value completion, then you get that value. This is, so just 17 produces an integer, just of something, or in general, a sender which produces just one set value with one argument produces the value. Because that value can have multiple arguments, so you basically get multiple results. If there are more than one result, multiple results, you get back a tuple. This is interestingly somewhat inconsistent with what sync-wait does. Sync-wait has a similar structure, like it also awaits a sender, which can also be like have just a just value completion, similar to these three, but it always returns an optional of a tuple of elements. So this, which is basically what you get out of the sync-wait if you get the result. So there's an inconsistency in the interface. The inconsistency over here is kind of annoying for generic programming, because depending on what kind of sender you await, you get a different shape back, and you may need to deal with that. However, I think it's unexpected, or although possible, that the task is templatized or generic on something which is actually co-awaited. Most users actually probably just write the sender they're actually interested in into the co-await, so they actually know the structure. So generic programming is not much of a concern over here. It's more of a concern for sync-wait, which may actually be reasonably used in a generic context. In which case, having one shape makes it much easier. So I think this is part of the reason for the yes.
Question. So, but as you like, I also wanted to ask about this inconsistency. But I think what you're saying, it's not because of your proposal, not because of task, but because of how co-await operator is specified in.
I will get to that. Yes.
Right? Okay.
Yes, I will get to that. I will just first describe what the result is and then explain how it comes about. There's also an error channel. If there's an error, like just error in fact actually only produces an error, but any sender which produces an error, you actually get an exception. We all love exceptions, it's great. So we catch them and we get the result out. Now, if you don't like exceptions, some people don't, you can transform, the way to deal with that is you transform the errors into a shape you feel more comfortable with. So maybe you want to get an expected out of that. So you could have an algorithm which takes a sender and turns that into an expected. You have to do so explicitly though. Part of the reason you have to do it explicit is there are other options, right? You may just run instead of an expected and optional may be more reasonable for use case or whatever it is. Unfortunately, as expected is not part of the standard library yet. I hope it will get in, or I imagine it will get into a future revision of the standard library. If you don't have it, it's not super hard to write. A simple version of that took me about half an hour. A full-blown version which covers all cases in all generality and all of that is probably more involved though, but it's entirely doable. Okay, and then finally, the last one, this is slightly weird behavior if you want, is we get cancelled. So just stopped is the indication that, or just stop produces a stopped completion, and then what happens with co-await over there? And the answer is the coroutine never resumes. That is, it's entirely, nothing happens to the coroutine anymore, it's just not getting there. So in that sense, it behaves like an exception, which you cannot catch, because the coroutine itself, even if it's not resumed, all the resources, any local variables, all of that gets properly destroyed. So there's no concern about, oh, I need to deal with destruction. There's no worry about that. It's just the coroutine does not get resumed at all. Okay. Now, the choices I just presented are actually not from the task proposal I wrote. They come entirely from the existing standard library. Yes?
Can you clarify about the resources? My understanding was if I do call wait,
Yes.
then the function is suspended.
Yes.
And so my understanding, if I had the local variables there, that would have, I don't know, a megabyte of memory allocated. That is leaked.
No.
Well, where's the destructible run if I
So-
do the call wait?
So if you have a local variable, the task holds on to that, right? So this is basically sitting in the coroutine frame somewhere.
Yeah.
And when whatever completion we do, the task will actually destroy the coroutine. That's basically an explicit call on the coroutine handle destroy.
When the destructor of a task will run.
Yes.
Thank you.
Yes. But it's definitely not leaked, right? So it's basically the memory is released actually kind of at a very early point as soon as the coroutine exits, right? Independent of whether we exit with an exception, whether it's kind of not resumed or...
This coroutine never exits.
It never exits, but it basically, maybe when exit is not the right term, maybe better to say when the completion is called, right? We invoke the completion on the next thing. Until that point, we actually need to hold on to that so that can travel over any results, but then it gets destroyed. The operation state is just released as for other senders as well. So there's no danger of a memory leak unless your memory allocation depends on non-RII destruction. Right? Obviously, if you allocate something over here and then free explicitly, then you will have a leak if it never resumes. Yes?
Yeah, so basically, task knows that the stopped signal completion that it got is terminal for the coroutine.
Yes.
You're done.
Yeah.
It didn't exit, but it's never going to be...
Correct.
So get rid of it.
Yes. Yes.
I'm pretty sure that's... I would bet some small amount of money that's not what's happening. I'm pretty sure you would, when the destructor of the task will run,
Yes.
then you would destroy the resources. But if you try to call await this task, it will not, just stop is not magic.
Well, if you call wait a task, right, it's just kind of chained again. The call wait a task will complete. At the point of when it completes, it releases its resources.
It will suspend, it will not complete.
It depends on the implementation.
No. Okay, so you need to distinguish between suspension and completion. The task always only completes while it is suspended. This is actually true whether independent on how you complete, because you cannot do anything to the task object while it is alive. You cannot destroy it. Right? You need to have it in suspended state. So when we come out of the task, whether we come out because we throw an exception or because we never resume on stopped, or we basically run to the end and co-return or implicitly co-return, the task goes into the coroutine goes into an suspended state. Then the completion is called, and as part of the completion process, the coroutine handle destroy is called.
Okay, thank you.
So moving on to why is the interface the way it is? And the answer to that is there's already with ptrans300 there's already an algorithm, asynchronous, which is pretty much just used. This takes a sender and turns the sender into an awaitable. It also needs a promise. The reason it needs a promise is effectively to do the cancellation business. There's an extra operation on the promise you have to implement for using asynchronous, which is something like called unhandled stopped or something. If that happens, you basically, the promise needs to decide what it does, and the task promise basically completes and, or I don't know in which order it does. It does it in the right order. It basically completes and calls destroy on the handle. So this is already existing. There were discussions about, oh, should we have additional transformations? Should we allow that if you have here a sender with a specific shape to have other results? And the answer to that was, roughly speaking, when I discussed that with people who have experience with coroutines in different contexts, in Folly, for example, said, oh, in Folly we did that. And everybody came and said, oh, this thing should produce this result. And so the net effect was that in this context, the Folly coroutine, the co-weight result was relatively hard to deduce what it is, and everybody wanted different things. So the conclusion is, we don't want that. We basically just go, if you want to transform it, transform it. Call as expected, call as variant, whatever you need, and just transform it. Okay. Now on to the next bit. Task also returns something. Over here, I just have a co-return in there. If there's also co-wait, a co-return without argument is implicit as well, behaves similar. So you can omit it, but you need any co-keyword. But so this guy basically implies that we return void. So it's equivalent to writing task or void. So the first template parameter of the task is actually the result type. And we can, instead of returning void, we could return an value. For example, this guy returns int, and then we get the integer out of the sync weight over here, as one would expect. Okay. Yes, so the task completion signatures. So because the task completion signatures define what is happening, I'm trying to put that together in a context over here. So task of void, the corresponding sender basically just has set value with no arguments. It also has set arrow with exception pointer and set stopped. Unless you do something special, this is basically what you get. You can also define a task of t, in which case it has set value of t, and then the co-return needs to match that, needs to return something which is convertible to t, as one would expect. Now, people also don't like the exception pointer and may want to produce other arrows as well. So the task has a second template parameter, and this is kind of the parameter where all kind of customizations go. By default, it has, well, all the customizations have defaults, and you can basically put something in and say, I want to override the arrow types and all the other defaults or other customizations you may inherit, just stay. So one of the customizations in there is the set of arrow types. So you can have an arrow completions and say, all right, my arrow completions, I don't want to have an exception pointer necessarily. I want to have set arrow of E and set arrow of F. And then the completion signatures become E and F. Of course, one of them can be exception pointer, but if neither of them is exception pointer, you get rid of exception pointer.
Quick question.
Yes.
So I assume that both template parameters have default template arguments, right?
Yes.
Okay.
Like the default over here is whatever it is, I don't know how I called it, but this basically sets up all kind of defaults.
M14.
And this is void.
Mm-hmm.
Yes. Okay, so obviously, if you actually set arrow types E and F, and none of them is exception pointer, the question is what happens if an exception is thrown? Well, the answer is simple. The program will terminate. You kind of said this guy is not having exceptions. Here it is. There's an exception similar to no except declaration in a sense. Sadly, it cannot statically be known whether an exception will be thrown. So I cannot make that a compile time error because based on just the task and its signature, you don't know how the body could look like. The same task can have entirely different, or the same task type can have entirely different bodies. And then the other thing is, which may be worth pointing out, the arrow types can be empty, in which case you just have no arrow completion. Okay, so now that I talked about being able to declare an arrow, how do we actually get an arrow out? Because that's the next question. So far we have only seen co-return as in producing a result, but if we actually want to produce a different arrow, we need to have a way to formulate that. And the way this is done is you co-yield this arrow of -1. So co-yield only understands this arrow at the moment. One could imagine in the future other things, but this is what it is. And it basically allows you to produce other arrows or whatever arrow type you need. So you can even produce different arrows. And this is just displaying over here. Okay, open arrow will just get the arrow and print it with, if you call it this 1. Okay, there was discussion why using co-yield. This is kind of weird. Wouldn't it be much nicer if we could just co-return this arrow? And yes, I considered that. I tried it. It doesn't work. Well, it does work, but it does not work when your coroutine has type void. The reason it does not work is kind of a little bit odd. The promise type needs to have a return value for the type you want to return. And it needs to have return void if you return void. Okay, so far so good. Unfortunately, a promise type cannot have both return value and return void. The compiler just says, nope, not having it. Which basically means this option would be constrained to have arrow types only if you actually want to return a non-void type. I don't think that is entirely reasonable. There's another option we could have used, and this is we could have used co-wait when arrow and produce an arrow out of that. I consider that to be confusing because normally co-wait is, all right, we wait for something to come to us rather than we return something else. So co-wait when arrow would be somewhat asymmetric. Yes?
Yeah, so what's the difference between co-yield with error and co-wait just error?
Co-wait just error results in throwing an exception. So you get an exception out of that.
Okay.
So this is, and the co-wait is actually not returning anything. It actually just, you await a sender and just error just happens to be a sender which immediately completes. So this is different and doesn't have the effect we want to achieve. Another option would have been, or the other option, which is what we used to say conceptually, it yields a value. So it actually makes sense, right? We yield an error. The caveat is most people expect that co-yield comes back, or you come back after a co-yield. But, well, this is not a requirement. And I think this is, out of these choices, so far the best one. There's another choice how you can get out of a coroutine, and that is throwing an exception. This, however, is exactly what I want to prevent to start with. So that is not a reasonable option at all. So co-yield seems to be the best option to me. All right. Then it's not because I'm at Bloomberg, but I want to talk about allocator support nonetheless. So the coroutine frame gets allocated somehow. Normally, if you don't do anything special, it gets allocated on the heap, just using operator new. But that may not always be a good choice. For example, in an environment where you actually cannot allocate at all, that you cannot do that. But you can actually do something different, and that is, if you have a coroutine, like C over here, with which is called with some arguments, you can get hold of these arguments in two places inside the coroutine. The first one is you can have an overloaded operator new, which takes these arguments. And this can be a template argument list. So there's a way to overload operator new, which gets hold of the arguments from your coroutine call. And then there's a second place, and that is the promise type kind of a constructor taking the same argument list. The arguments actually passed are slightly different in the sense of these guys going into operator new are really references to the parameter list. These guys over here are references to a copy of the or move of the parameter list, right? Depending on whether our L values. So there are different objects, but they are semantically meant to be the same. So this can be used to stick an allocator in. And the idea over there is pretty much to say, first of all, to declare that we want to have allocator support. The way to do that is in the context parameter, we would declare an allocator type to whatever allocator type you want. The default allocator, I can go, oh, I always have an allocator. Yeah, sure, but the default allocator is stateless and just calls operator new directly. This is not a cost. So the default is just fine. And if you don't want to have, if you want to specify an allocator, you basically use allocator arg t parameter, and the coroutine fishes out the argument coming right after that to say, this is my allocator. Well, this is the argument I use to construct the allocator. So the argument which comes after the allocator t does not have to be of type allocator type. It can be, for example, a memory resource, where the allocator type is polymorphic allocator. That's fine. It just needs to initializes that and uses this allocator then to manage memory. So to yes, there's a little bit of a detour. When implementing that, you go kind of, all right, great. So we fish out the allocator, we have an allocator in hand, we can call operator new. Now we get deleted. Now, how does operator delete work? Well, we get an object, and we somehow need to find from the pointer of the object, which is of type void, where the allocator is. And normally the pointer to object is not only don't you know the type, but you also don't know anything about that, right? And it is destroyed. But there's actually something which I was not aware of before I embarked on that work. There's an operator delete, where you can pass a destroying delete t. If you have an overload like that, you get a pointer of your enclosing class type t, and this points to a non-destroyed object. So you actually get a live object, and the contract on this operator delete is you destroy the object and release a memory. But you could, for example, take the object and ask the object about its allocator. The allocator can be stored in the object, and you don't need any fuffing about. So I thought, hey, that's great. Let's try that. Unfortunately, it doesn't work with promise types. The reason it doesn't work with promise types is the promise type is actually never allocated directly. It is just a member of the coroutine frame somewhere. And just because you have an operator delete for the promise type does not mean you get an operator delete for the coroutine frame, which is somewhat annoying. So it took me a little while until I managed to create an operator delete. The way to actually do it is you get a pointer and a size. So you can use the size information to say, right, I store the allocator after size, and I get it from there. It's ugly. I don't know whether it's actually fully conforming or, but this is what the implementation is supposed to do. Yes?
I remember there's something like from promise. Does it not help you to get the coroutine from promise?
This could help us if the operator delete with a destroying argument were called with a handle thingy or a pointer to handle or something, but it isn't. I just get the operator, there's no, or at least none of the compilers called a destroying delete, even though I basically made that parameter a template argument. So, and I cannot formulate the coroutine frame type because I don't know it. So if we had that, maybe that would work, but we don't have that.
Makes sense. Thank you.
Okay. Yeah, here's an example of how that could look like. So this allocator is just my context type, where I say allocator type is polymorphic allocator of bytes. And then I just use a task with that. Now, when using a coroutine, this optional allocator support, one way I find kind of cute is you basically pass this as a trailing list of arguments. These are the arguments you don't care about. These are arguments to the coroutine mechanism. And this actually doesn't use allocator yet, really. Well, wait, I do use allocator argt of new delete resource, which actually, oh no, it does use it. Okay, fine. So, which basically constructs an allocator of this type, and all the allocations for the coroutine frame are done with this allocator. To actually, there's a way to get it out. So readenv is just a mechanism to read a property from an environment. The environment over here, the query for the environment is getAllocator. So readenv is a sender which reads the allocator. It needs to be a sender because the interface into the coroutine mechanisms is effectively co-await. So you basically this turns the query into a sender to then extract the allocator. I don't mention that over here. If you need the allocator, you could have passed that by argument, but the sender over here, which is used, can be some other nested sender, and the allocator is exposed over there. Which I think brings me to talking a little bit about the environment hold in the promise type. So this will get a little bit more populated, but basically inside the coroutine frame, we have the promise, and this can hold the allocator because we actually saw that.
Dietmar,
Yes.
why do you need to co-await on readenv?
Well, let's say I tried to just use getAllocator directly.
Okay.
Right? I could try that as a function, but this function doesn't have any access to the environment. I need a place to get hold of the environment. And the environment basically is passed in. The promise type pretty much creates a receiver which references the promise as an environment. And this is how the environment is channeled in.
Yeah, that answers my questions, but they're not obvious.
It's fine.
You could probably do some template programming to pull it out of the args that you were getting.
Yes.
You don't have a name for it without doing it.
Sure. This is what I said. Like for the coroutine over here, it doesn't make much sense, right? You can fish it out of these arguments if present, using the same logic the coroutine has. But readenv is already a sender, which is going where there may be other things wrapped around. This is actually just to show the allocator is part of the environment passed to the sender. So basically,
even better.
Right. Yes.
I don't know. So execution read environment is a thing from the standard senders.
Yes. Execution readenv is a standard sender. Execution getAllocator is a standard query. So they're both part of the sender receiver proposal. Well, readenv is part of a fix. It used to be an exposition only thing, I believe. Okay, so yes, let's go on to the next thing. Cancellation, super important. Now, how do we cancel things? And there's a similar thing. You can basically get a stop token from an environment. So the coroutine provides an environment which will contain a stop token. And this one you don't have any other access to other than asking it for an environment. And this is just showing right, let's say my coroutine wants to run a loop, and eventually we want to kill it. Basically, the stop token is connected to a stop source. We call request stop on the stop source, and the same completes with set stopped. Well, actually, this one doesn't say it doesn't stop with set stopped. This actually just listens to it and then actually completes successfully with void. Sorry.
Question. Does every task contain an in-place stop source?
We get to that on the next slide. The answer to that is yes, no-ish. You can control that. And I will explain the reason why you can control it. But we'll try to do that with a little bit of graphics. So the original state to get anything cancelled in our string must come from the receiver the operation state holds. So far, so good. So the state of our coroutine or whatever is using the coroutine wants to get the token. So the token could reference that source directly. There's however a problem, and that is the type of the source is not known when we create the coroutine. The type is only known once we have connected these things. But the type spelled out in the code has to be defined when we define the coroutine. So if these types match, great. If they don't match, we need to kind of type erase this type. Correspondingly, the coroutine can contain a source, and we can reference that source if we have to. If we don't have to, we actually may still want to reference the other source. Like if the type of this source and that source are identical, this token can either go here or there. And the reason it is relevant to possibly go to the outer source is to basically recognize that the outer source gets stopped in the thing that if it is connected to the inner source, we basically need to hook up a callback. And there's cost involved in registering and deregistering a callback. So we may want to avoid that. So we can directly connect that. And to do all of that and control the stop sources you have, you can define the stop source type and basically say, all right, this is the type which comes back from that. And the task can then go, if it gets a stop source matching that type, it can just forward directly without using its internal stop source. If the types mismatch, you need to go through the internal mismatch. And then there's the potential that you say, well, but I don't want to have stop source at all. Fine. You can actually entirely disable it, in which case you also cannot ask for the stop source. And you can ask for a stop source, but you get something like a no stop token or something. So you can get rid of the source. If you want to, you can control it. And by default, it is an inline stop source. I hope this answers Kirk's question. Yes, let's go.
Just to clarify, so coroutines through the core wait mechanisms on the outside pass to each other this environment thing.
Yes. Yes. So it's basically senders always have or receivers have an environment, and the coroutine task provides a receiver which references an environment which is used to channel all kind of information through.
Thank you.
Yes.
Just making sure I'm reading this correctly, this will complete on the value channel. If I wanted it to advertise that it's stopped, I would need to, like at the bottom, co-await or
Yes.
Yeah.
If you wanted to actually stop with a set stopped, you would go, you never drop out. Otherwise, you would have a co-await set stopped. Co-await just stopped. So you can terminate.
Communicate.
Yes, you can communicate that outside.
But yes. This doesn't.
This actually does not. Yes.
Okay, which is
fine. Slideware. Right?
Well, slideware, and that might be fine anyway.
Yes. Okay, this slide pretty much just talks about what I just said. So cancellation is super important, and so stop talking is important, and you can control it. Okay, moving on to actually, what about user-defined queries? So far we have seen that we can control the allocator, or we get an allocator from the environment and a stop source. But you may have an environment get v over here, which the implementation has no clue about. This is only how to define an query, so that it plugs into the readenv mechanism. It requires basically that you have an operator, a function call operator with your environment type, which has no arguments, and that just gets queried. So, and then you want to have this query thingy. Oh yeah, sorry. The query down here is a decision whether this environment is forwarded when you wrap it. So it's basically forwarding query, maybe set to true. You can set it to false, in which case it does not get forwarded when wrapped, which is typically not that useful and not useful for what I'm talking about over here. So what happens if I query that? If I readenv get v, well, this produces an error because the context, there's no context specified, that doesn't know about this query at all. So we can change that. We can basically go and say, all right, let's give our query, our context, actually a way to answer that query. So we just say query get v t and return a value. Now that's not particularly useful because this is just 0 initialized, so you always get 0 back. But just to show the mechanism, this is how we could get that. Now the next question is, can we get it also initialized? And the answer to that is yes. And that is the context actually gets or can get an environment passed if you want to. And this environment is not the environment from the coroutine. It is the environment from the receiver connected to the task originally. So it's kind of the outer environment. You may not necessarily know what type that is, but if you know that this guy has a get v query, you could basically go, right, I query that thing. So this is basically outside the type erasure thing. Of course, this produces an error because I've not done anything to set an environment to have a get v. But I can fix that by just saying, all right, I use makeenv to create an environment which has a get v query, and I create writenv to actually produce a sender which has this environment. And then I think, did I forgot? I think I forgot the task in here. Oh no, sorry, no.
With env.
With env, right? There's no with env
That's
in there.
with it. No.
Oh, there it is. Yeah. Sorry. Yes, that's with env. Sorry. So this guy is in the end called with this environment being passed into the outer receiver. So we get hold of the getEnv over here. So we can pass that through. So this is the way to expose an environment if you don't need to store anything you don't know about. Like over here, we basically go, all right, we know the type, we get access, we can just write integer over here. But we may not know that type. So it can get a little bit more complicated, but before showing that is basically just kind of the environment over here. It means there's an environment living over here, and we expose that into our thing. But we can also have a user-defined context where we actually don't know the type. So where we go, all right, we have some kind of environment, we pass that through, and we could capture something depending on the type of the environment. We probably need still some type erased access, because eventually when it's called this readenv, the type needs to be known. But we can store something which somehow depends on the environment type. And this entity, if something like that exists, like if there's an env type in the in the context. So fancy is just the context I wanted to pass in, and I didn't fix that. No, it did. So fancy is just this context type we pass in. If that has a nested env type, it tries to construct that thing, and you can do other fancy things because you get the concrete type and you can store something. It holds onto that in the operation state object. Okay. On to the actual, everybody agrees that that is needed part, and this is where do coroutines resume. This is, slightly interesting. So there's also an environment query to get a scheduler. So basically, when we start the coroutine, it is expected that we run on an original scheduler. And this is basically coming from the outer environment. Now, we could co-await something like schedule with a scheduler and then do something. The then over here is quite obvious. This is just sender logic. This has nothing to do with the coroutine. So schedule completes on the corresponding scheduler. So then this guy is executed on that scheduler. So far, so good. Now we have a co-await of that thing. And the question becomes, does co-await complete on original scheduler or scheduler? I'm not posing that as a question because this is just kind of, there's a choice and both choices are reasonable. The choice task does is by default, you execute on the original scheduler. This means you get rescheduled somewhere. Let's say you complete on an IO scheduler with something. The next line is executed on the original scheduler. That's basically a scheduling back, queuing things, getting it out. So there's some inefficiency in here, potentially.
But gets rid of a whole class of bugs that people write by accident.
Yes. Yes. And everybody who tells me that they have an async interface where things complete wherever they complete and you give control back to the user back there, whether it's via coroutines or a callback, doesn't really matter. If you do that, there are lots of errors. So the people who have experience with coroutines at scale, at Folly and Unifex, and to some extent stdexec said, this has to reschedule. Not rescheduling, not having scheduler affinity is a bug farm. Yes?
Okay. I saw, I think in Microsoft, some of the stuff you can say call wait background thread or something. Can I say call wait schedule me on the background thread?
So you can, this is on the next slide, you can avoid going to a different scheduler. You can basically, let's just show it. So one thing you could do is you could actually, instead of directly co-awaiting something, you can co-await change coroutine scheduler with whatever scheduler you want to co-await. On which you want to resume. So if you have an inline scheduler, the inline scheduler basically just completes immediately when started on whatever context it is. So this would be now executed on the on sched. So it doesn't reschedule. Inline scheduler in this context is actually an exposed and known name. The reason for that is the rescheduling logic over here, something like continuous on. Actually, it's used a fine on. Can decide based on seeing an inline scheduler that it can entirely say, all right, the scheduler I'm going to go to is entirely not doing anything. So it can remove any mechanism being there. So it's entirely optimized out. If you write your own inline scheduler, it semantically works, but it may be a little bit slower because there's still some mechanism being set up. The other important part over here is, I didn't have space on the slide though, this sender over here returns the original sender back. Although not with the correct type, it will be a polymorphic a type erased scheduler called a star scheduler, but you get the scheduler back. So you can go, don't want to reschedule on that scheduler for some work, and it can then restore the original scheduler if you're so inclined. There was a question whether it should be possible to have an RAII thingy to restore that, but to some extent, well, this is not really a resource. And falling off the end while not restoring it does not matter because nobody is looking at what is being restored over here. So the proposal I have does not contain an RAII facility to restore the thing. You could do it. I think it's borderline easier to write it with just capturing that thing and calling change routine coroutine scheduler again. Okay?
Question.
Yes.
So, where is change coroutine scheduler? Is it in your proposal?
Yes.
Okay.
Yes. There's something new which doesn't exist.
It says like std execution change coroutine scheduler.
Yeah, obviously omitted namespaces all over.
Yeah, but that's why I'm asking. It's purpose to the fit on the slide. I understand it, but I need to know where to take this API from. And it's in your proposal. Okay.
It is in my proposal, and it would go into std execution. So the proposal overall basically defines three entities, I think. Inline scheduler, something called task scheduler, which you can use as a type array scheduler if you want to. It was originally called any scheduler in the context of, all right, this is just a type array scheduler everybody can use. But there were concerns saying, oh, but it's not fully generic and it doesn't deal with who knows what. I didn't quite understand the use case even. But there may be use case, and there was objection to calling it any scheduler. So it's called task scheduler, which doesn't say specific to the task. It's just pick a different name. And then the other entity is task. Okay, cool. Then, because, hey, we have a context, we can do it possibly even fancier. We can also define in the context, we can have an inline context, for example, where we set the scheduler type to be inline scheduler. And then no scheduler affinity is happening over here at all. This also means that the internally stored scheduler is an inline scheduler. So you actually probably cannot replace it unless the inline scheduler actually, or whatever scheduler, has a replaceability feature. It has also the implication that if you use an inline scheduler over here from the outside, that the task does not, well, it will try to see whether it has an interface based on get scheduler on the type and try to initialize it. But if that doesn't work, it's fine over here because we can default construct an inline scheduler. If you use the default task scheduler, the implication is that the outer receiver actually needs to provide a scheduler, which is sadly not always the case. In particular, when you put something into a scope, the scope starts things, it doesn't know about scheduling, so there's no scheduler in there. Which means to use a task with a scope, you need to have a little bit of a right env and stick a scheduler in, unless we also create another algorithm to do that. Okay, and actually, I just got a sign that I still have 30 minutes, but I'm actually done. So there are resources that's fully implemented as part of the Beeman project. And this is a proposal for things. And I'm happy to discuss all the design decisions and hear about other things where you go kind of, oh, you're missing this crucial feature or this feature which is important to me. Yes?
Yeah, I wanted to ask, so the biggest issue with fully task, and I think Google had the same problem, is lifetimes. So when you are co-awaiting a task immediately, you're okay. But as long as you start doing something if you just create a task as a variable and do something later, your argument might disappear. And this is really causes a lot of bugs. So people are considering different options, like Google had this code thing where they have not just a task, but a different type. Have you looked into something like that?
I haven't looked into anything like that. And so the coroutine mechanism obviously captures all the variables. Now, if you capture anything over there by reference, you're probably in a world of pain no matter what you do.
If you
Right.
have if you call wait immediately, it
Yes.
doesn't matter that you pass the referencing.
Yes, because it lives long enough. Yes, I agree with that. But yes, you need. If you don't do that, this issue is not addressed over here, and I don't see that how to address it reasonably.
All right.
So yes,
So, why have you decided to call the second template parameter as context? Does it have any commonality with execution context?
it doesn't have any commonality with execution context, and well, it's just a template parameter name which you actually never name, right?
Okay, but still, I mean, you presented as a context, and I found it confusing. That's why I
Okay.
asked this question. But we can discuss it like later, how to better call it. Like, but what is the semantics? Is it like configuration of your task
This
or
is
something like that?
it is actually two things.
Okay.
Maybe it would be better named environment in a sense, but it's not just environment. So it's partly configuration. So for example, the allocator type, but it's also the place where any user-defined environment actually gets stored. So
So still environment, huh?
fine. Okay, so I will seek renaming it to environment. That's fine.
Okay.
I don't have any opinion on that name. It never shows up in code the user writes.
Yeah, but it will appear on something like CPP reference,
Sure.
right?
Yes.
Which is like also like
Yeah.
teaching resource.
Yeah, fair enough.
And they might be confused by that, as was I.
Yes, okay. Sorry for the confusion. I will try to remember renaming it to environment.
Can
Yes.
we go back a couple slides, just thinking about scheduler affinity? Can we go
Okay.
back just a couple more? Where we were first. Yeah, here we are.
Something like
So, who's? So
Okay.
yeah, this is perfect. Who's responsible for getting us back to the original schedule? So you have a co-wait operator, and you have the schedule object.
Mhm.
Where's the logic for rescheduling us back on the original scheduler?
Mhm,
living?
okay. So basically, the rescheduling happens in what's called await transform.
Mhm, yeah, I'm familiar with co-wait transform.
So, and await transform is implemented effectively as a fine on the scheduler we get,
Yes.
and as what's the other one? As available.
Mhm.
So this is all it is. So there's basically an algorithm.
So because co-wait transform knows about schedule,
Yes.
and whatever it's getting transformed into, that thing is going to be responsible for getting us back to the original schedule.
Yes.
So I could
You have no control over what happens.
I could
in there.
hijack this, is I guess my point, right? I can co-wait something that doesn't know that it's supposed to get me back to the original scheduler.
No. Because whatever you co-await is the argument into await transform,
Okay.
and this will be wrapped with get me back elsewhere.
Okay. And then this is checking something in the task
It,
object to figure out what scheduler behavior I want, because I can change this to the inline scheduler.
it basically just uses the scheduler which is currently stored in the task. It just
Got
goes take this
Okay, and
type
if the
array
inline
scheduler.
scheduler just says don't do anything, it just says wherever I ended up, leave me
Yes.
there. Okay, understood.
Yes. And one thing which I haven't quite discussed actually, but as a discussion brought that out, the algorithm over there which is wrapped around is called affine on, rather than originally I had just used continuous on. And then people said, well, maybe we have ways to avoid the scheduling. We could, for example, detect that for example, in the case of like something like co-wait readenv, the readenv is executing, is completing synchronously. There's no need to reschedule that. So we could have a property in the future when we define it, or implementation specific on the thing saying, oh, this does not change scheduling. So you don't need to do anything.
Yeah.
There's, of course, a caveat with that. If you always complete synchronously and you do that possibly in a loop, you may Stack Overflow. Because the co-waits basically just call the next thing. The loop is not really unbound. If that does not reschedule, you basically just call the completions, more completions, more completions. And that is not, this is sadly not
Okay,
tail
so
recursive. and you also cannot use the asymmetric transfer.
Right, and because senders, although logically you could do the tail call optimization, that turns out to generate bugs.
And yeah, they're kind of not, yes.
It's like, logically you could, but because of C++ semantics, this also ends up making the references that you think should still be live be dead.
Okay, maybe.
I talked to Derek about it at some point.
That I would need to think
But
through
that's on
deeper.
the
That I don't know.
that's on the sender's side.
But this is entirely separate. The only warning is if you don't reschedule, you may get a stack overflow. There's an algorithm where we want to control these things, and there are other reasons why we may not want to reschedule as well.
And what happens if you, let's say, like your environment doesn't have the property which is getScheduler?
If there's no getScheduler in the outer environment, and it needs that for the scheduler which is used, it will be a compile time error.
Okay.
Because
can you use it like without it? Like, can you just go wait on the scheduler that comes to your argument and like, or do you always need to read it?
Well, the thing is, by default, it always does the rescheduling using affine on, but it actually always uses affine on, except when using inline scheduler where the affine on is avoided. But otherwise, it always does it, and it always has a scheduler. And the question is, what does that scheduler do, right? If you inject from the outside a scheduler which doesn't do anything, this is another way how you can avoid scheduler affinity. But then, in a sense, if the scheduler coming from the outside is the inline scheduler, it's scheduler affine to the inline scheduler, which isn't particularly useful. Yes.
Just for FYI, I
Sure.
found so there was last year's talk by Aaron Jacobs, C++ coroutines implementation at Google,
Okay.
where they really tried to address the lifetime thing.
Okay.
So maybe check this out if it implies what
All right.
you think.
Thanks. Yes.
So if I've understood, it's like, in order to get that compile error, I would basically have to like construct a context environment, whatever, that's missing things that this is like, the one I'd get if I didn't ask for anything does the right things.
Yes, the one you get. So the way it works is the scheduler type is basically just constructed, and while constructing it, it first tries does constructing that scheduler with getEnv from the receiver work. If that works, it uses that.
Mm-hmm.
If that does not work, it tries to default construct the scheduler. And this may or may not work. And for the task scheduler, it deliberately does not work. It does not have a default constructor, so that you have to inject a scheduler if you don't have one.
If you want that kind of behavior.
Well,
but if I don't do anything,
if you don't do anything and you don't provide a scheduler, it will not compile.
Yeah,
if you provide a scheduler, it basically wraps that scheduler into the stars scheduler and uses that. So I think that is kind of reasonable.
Yeah, it's like it probably helps. It's like playing with schedulers. I've found programmers create more bugs than they avoid by it. It's like
probably
this probably doesn't have the larger context it needs to figure out what scheduler it should be. Except like we've now avoided the callback problem where I'm getting called back on the IO thread. All I should do is copy my values and get back to my own.
Yes.
But that's
yes. But this does it implicitly.
It does it implicitly.
And just to be clear, it does not hook on schedule over here in any shape or form. What that hooks on, this is basically just saying, all right, this is completing somewhere else. If you have whatever sender, and this does complete on a different thing, it still does that because it always wraps around this affine on to go back to the scheduler. Yes.
So, more generic question. So basically, in your examples, you exposed like primitives from P2300 a lot. So the question is your task basically for senders and like integration of senders and receivers and coroutine only, or is it useful for anything else beyond this world?
Well, it is a sender itself. So if you don't play with senders, this task wouldn't help you. But then I don't know how a task would look like if you don't have senders. Well, you could have a like the original lazy proposal, which had a bare bones thing and had some way to execute that. But you need all of those things because you need to hold on to the task and actually start it somehow. It's always executing lazy. And sender receiver has a vocabulary to do that.
Yeah,
in my mind. So
yes, I understand. So basically, the answer is it completes the story with
Yes.
senders and receivers and coroutines.
yes,
Okay.
yes, it integrates coroutines with sender receiver, and is another one of the, in my mind, super crucial toolboxes in the sender receiver world.
Yeah, I think you touched on this, but like this replaces like the any sender that we didn't get at first because it does the type erasure that we need.
Yes, that it does as well. But you
It's
could just have a co-weight, the entire body could just be co-weight some sender, and then you have effectively an any sender entity produced. You could use that is a separate tool.
and probably also replaces a whole bunch of use cases where I might otherwise want to write a sender of my own.
Yes, and this is in my mind the way more common thing that you write some algorithm and it's more readable to most people to write it over here.
It's going to be easier to get correct because
It's probably easier to, well, that I don't know. But it's more readable to most people, and maybe that's as a result easier.
I read my own code.
It is, however, has a chance to be also slower. Like you need to store the value to go then into await resume, right, to get it back and the stuff.
Yeah,
So writing a coroutine.
couple of these, it's like there's a lot of machinery
Yes.
to write a sender, and
Well-
if you get in, you can avoid doing some of it, but then you also pay a penalty for not doing those.
Well, what I'm trying to say here, however, is the machinery for writing a sender is actually not that bad, and the compiler can probably quite well understand that. The machinery for coroutine is actually way more involved, and I doubt that the compilers are as effective as they would be in senders.
Probably.
So I imagine that people who have written things with a coroutine, and that turns out to be part of a performance critical thing, to rewrite it as a sender and get a performance improvement.
Yeah, it's like it's more automatically transparent. But since I'm putting words in vendors' mouths here, it's like compilers already have to know lots of details about coroutines and how they work. They just have not been pressed to make it better.
Yes, maybe. So I don't know. I actually don't know if it's bad, really. I've not measured performance of that thing. I wanted to get the semantics out.
It's like working is a good start.
Yes. Okay, cool. Anything else? Otherwise, thank you very much.